Hey everybody, this is Mrs. Mancuso. I am going to go through this Wednesday work with you. Today we are working on gas law calculations. So you will remember that we just have one formula. So our formula is P1 V1 over T1 equals P2 V2 over T2. So this is the combined gas law formula. So gases are affected by pressure, volume, and temperature, and you can change any of these factors and see how it affects the other and actually calculate it. Some important rules: make sure the temperature is always in Kelvin. So if you're given Celsius, you got to add 273 to give you a temperature that's in Kelvin. STP refers to standard temperature and pressure, and those values are on table A. I like everyone to be in the habit of identifying these values, P1, P2, all those things, in the question and label them right in the question. Cross multiply to solve for X. Whatever algebra math skills you have, bring it to the table and use that to solve. If necessary, so if it's not a whole number, which it very often is not, round your answers to the 10th place, check your units, and show all your work. So let's go ahead and get started here. If I have 21 liters of gas, so that's my first volume, so I mark it with a V1, held at a pressure of 78 atm, so that's my first pressure, and a temperature of 900 K, so that's my first temperature. What will be the volume of the gas if I decrease the pressure to 45, so that's our second pressure, and decrease the temperature to this? All right, so my first pressure is 78 and my first volume is 21 over the first temperature, which is 900, equals, all right, the second pressure is 45. I'm going to solve for V2. That's my X in the problem. And on the bottom, I have 750. So I have not written the formula, but again, all I did was fill in this P1 V1 over T1 equals P2 V2 over T2. You can write the formula every time if it helps you. All right, now on to the algebra. So I prefer to cross multiply. I want V2 to be by itself, so I'm going to leave V2 right there. I'm going to cross the 45 down and multiply it by 900, and I'm going to cross the 750 up. So let me rewrite it. 78 times 21 times 750 divided by 900 times 45 is going to give me V2. So I'm going to go ahead and do that math. So I punch in the calculator, 78 times 21 times 750 equals, and now I divide by 900 equals, divide by 45 equals. So that's another way. If you have just I just have a little 4-function tiny calculator from the classroom here, that's how you can solve it. So 30.3, and then volume was in liters, so my answer is in liters, and I rounded it to the 10th place. All right, moving on to the next one. If I have 2.9 liters of gas, so that's my first volume, at a pressure of 5 atmospheres, so that's my first pressure, and a temperature of 50 Celsius. So I'm right away in my calculator going 273 plus 50 gives me 323 K is my T1. All right, what will be the temperature of the gas if I decrease the volume to this? So that's my V2 and that's my P2. All right, so 5.0 times 2.9 over 323 equals 3.0 times 2.4 over T2. Now it's T2 that I want alone, and I want it on top. So I'm going to throw T2 up there, 2.9 and 5.0 I'm going to put down there, and 323 over there. That way T2 is by itself. So here's T2 by itself. I've got 323 times 3.0 times 2.4 divided by 5.0 times 2.9 equals. All right, so I'm punching it all in the calculator. And again, if you have a graphing calculator, you can actually punch in all the parentheses. I think it's just as easy to go 323 times, I hit the wrong number, 323 times 3 times 2.4 equals, divided by 5 equals divided by 2.9. So I can divide it by each of those numbers separately, and I'm going to get the same answer. So I get, wait, I think I did something wrong. I'm going to do it one more time because I got a huge number. 323 times 3 times 2.4 equals, and then divided by 5 equals, divided by 2.9 equals. Okay, that makes more sense. 160.4. And then my temperature is always in K for these problems, so there's my unit. All right, next problem. I have an unknown volume of gas held at a temperature of 115 K in a container with a pressure of 60. All right, so I do not know V1. So that's weird, but I'm starting with my unknown being my very first thing. So V1 is what I'm going to solve for. The temperature is already in Kelvin and the pressure is in ATM. If by increasing the temperature to 225 K, so this is going to be my T2, and decreasing the pressure, so that's my P2, causes the volume. Okay, so my first pressure is 60, so 60 times V1. That looks so messy. Hang on. All right, 60 times V1 over the first temperature is 115 equals the second pressure is 30 times 29 over the second temperature is 225. All right, I want V1 to be alone, so I'm going to move the 60, cross it down, the 115, cross it up. So V1 is equal to 115 times 30 times 29 divided by 60 times 225. Okay, 115 times 30 times 29 equals, divided by 60 equals, divided by 225. All right, I get 7.4. And then my unit is liters. So let's just think about it for a second in terms of a gas. So it was very cold. I heated it up. So when it was hotter, it was a larger volume. And the pressure was 60 at the beginning and 30 at the end. So it should be a much smaller volume, which it is. So that makes sense. All right, how hot will a 2.3 liter balloon have to get to expand to a volume of 400 liters? So if I want it to expand to that, that's going to be my second volume. And this was my first volume. So it was 2.3 and I'm expanding it to 400. Oh my gosh, this is an insane balloon because it must have so much elasticity to not pop. 25 degrees Celsius. Okay, I want to add 273 right away. So 273 plus 25 gives me 298. And that's my T1. Okay, so 2.3 over 298. You'll notice the pressure is staying the same because it's not giving me the pressure in the formula. So I can just cross off the P's. I don't need them. That's why this combined gas law, you can just use what you have and cancel out two of the same factor, one from each side. All right, the second volume is 400 over T2. This is going to have to get crazy hot. So I want the T to be on the top, so I'm going to move it up there. I'm going to move the 2.3 down, and I'm going to move the 2.98 or 298 up. So T2 is equal to 298 times 400 divided by 2.3. Yep, definitely going to be a huge number. 298 times 400 equals, divided by 2.3 equals 51,826 K. Insane. All right, I have a thermometer which measures temperature by the compressing and expanding of gas in a piston. I have measured that at 100 degrees Celsius. All right, so right away I got to go. Plus 273 would be 373 K. So that's my T1. The volume is this, so that's my V1. What is the temperature outside if the piston has a volume of 15? So that's my V2. What would be appropriate clothing for the weather? All right. So my first volume is 20.0. Again, I don't have pressure in this one, so I don't need to include it. 15 over T2. And I'm going to solve for T2. So I move T2 up. So T2 is going to be equal to 373 times 15 over 20.0. So 373 times 15 equals, divided by 20 equals 279.75 K. All right, now just to humor us, I'm going to go 279.75 minus 273 is equal to 6 degrees Celsius. So it's extremely cold out. And so 6 degrees Celsius, you are dressing warm. All right, next one. Submarines need to be extremely strong to withstand the extremely high pressure of water pushing down on them. An experimental research submarine with a volume of this, okay, so that's my V1, has an internal pressure. All right, so that's my P1. If the pressure of the ocean breaks the submarine, forming a bubble with a pressure of this pushing on it, so that's my P2, what will the volume of that bubble be? So what's V2? So I have no temperature, so I don't need any temperature in this. I just have P1 times V1. So 1.2 times 15,000 equals 250 times V2. I'm going to divide this side by 250, divide this side by 250. Now V2 is by itself. All right, so 1.2 times 15,000 equals, and then divided by 250 equals. All right, the second volume is going to be 72, and then the unit was liters, so this is liters. So there it is. Next one, divers get the bends if they come up too fast because gas in their blood expands, forming bubbles in their blood. If a diver has this many liters, so that's going to be my V1 of gas under a pressure of this, so that's my P1, then rises instantaneously to a depth where his pressure is this. What will be the volume? Oh, so the volume is going to expand quite a bit, so that's why it's a problem. All right, so we've got no temperature again, so we've got 250 times 0.050 equals 50 times V2. Again, to do it, you can cross multiply or you can just divide both sides by 50. So 250 times 0.05 equals, divided by 50 equals 0.25. So that's quite an expansion to go from 0.05 to 0.25. And this is liters. All right. If I have 15 liters of gas, so that's my first volume, at a pressure of this, so that's my first pressure, and a temperature, okay, so I got to add 273, 150 plus 273. So every time I see Celsius, I'm going to just quickly add 273 to it. I get 423 K, so that's my first temperature. What will be the temperature of the gas? So I'm going to solve for T2. If I decrease the volume, so that's my V2, and the pressure to this. Okay, let's fill them all in. First pressure is 4.0, first volume is 15, first temperature is 423. The second pressure is 3.0, the second volume is 12, and T2 is what I'm solving for. All right, I want to cross multiply. I want T2 to be by itself up here. I want these two to get out of here, so they're going to cross multiply down, and this is going to cross up. So T2 is going to equal 423 times 3.0 times 12 over 4.0 times 15. All right, 423 times 3 times 12 equals, divided by 4 equals, divided by 15 equals 253.8, and then now I know T is always temperature, and temperature for all my gas problems is in K. All right, next one. If I have 2.6 liters of gas, so that's my first volume, held at a pressure of that, so that's my P1, and a temperature of this, that's my first temperature, what will be the volume of the gas if it's at STP? So I look on table A, standard temperature is 273 K, and standard pressure, I have two options, 101.3 kilopascals or 1 atmosphere. I always have to use the same unit as what the question used. So the question was in kilopascals. So my second pressure is 101.3 kilopascals. All right, so I have 130 times 2.6 over 900 equals, the second pressure is 101.3. V2 is what I'm going to solve for, and the second temperature is 273. I want V2 to be alone, so I'm going to cross this down and cross this up. So I have 130 times 2.6 times 273 divided by 900 times 101.3 equals V2. All right, let's do the math. 130 times 2.6 times 273 equals, divided by 900 equals, and divided by 101.3 equals. All right, so my second volume is going to be 1.0. So I only have 1 liter of this because I've cooled it down so much it has compressed down to just 1 liter. All right, last problem, you guys. All right, how hot will a 4-liter balloon have to get? So if I have a 4-liter balloon, that's my first volume, and it's going to expand to 16 liters. So that's my second volume. Assume that the initial temperature is 30 degrees Celsius. Okay, plus 273 is 303 K. Pressure remains constant. Okay, so 4 liters at 303 is equal to 16 liters at what temperature? So this one's pretty easy. I'm actually just quadrupling it. I'm multiplying it by 4. But I'll go ahead and set it up like normal. So if I want T2 to be by itself, that's going to equal 303 times 16 divided by 4. So 303 times 16 equals, divided by 4 equals 1212. All right. For the sake of math, because chemistry really is applied math, and you might look at this and go, well, you're just quadrupling it. If I had taken 303 and multiplied it by 4, I would have gotten 1212. So I would have gotten the same answer. So always trust your algebra mind. You will have no problem solving these if you just think through the algebra of how to solve the problem. All right. And let's see, where did my little... there we go. Have a great day, everybody.